Hello, GopherCon. I hope everyone here is having a great time. My name is Holly Castello. It's my first time attending. It's such an honor to be part of the community and to be invited here as a speaker. Today, I will present a project I did with my colleague Yukong at my previous job. I have since then decided to go full time to get my PhD finished. It's been taking such a long time. This project, believe it or not, was actually inspired by a German physicist, Werner Heisenberg. Is anyone here familiar with Heisenberg and his uncertainty principle? Okay, good. Thank you. Heisenberg, in his uncertainty principle, stated that you cannot simultaneously observe the exact position and the momentum of a particle. Since particles are moving around constantly, the more you try to accurately measure one, the more you are disturbing the other, and therefore less accurate measurement you're getting for the other. The analogy we draw from his theory to system performance monitoring is that the very act of observing a system's performance actually adds overhead to the system and then alters the system's performance. So just as this anonymous has put, you can observe a system, but be prepared for it to act like it knows that you're observing. So as much as we wanted to monitor a system's performance in order to improve the performance, if we don't do it carefully, we might be getting a not at all accurate observance, and then even worse, hurt the system's performance. So before we began the project, we actually did a CPU profiling of this trading system that we were working on. So here's a question for you. Which one of the following was the actual percentage of CPU allocated to performance monitoring related work? Is it 0.01% or 5%, 35% or 55%? The answer, unfortunately, was 35%. I'm sure everyone here would agree with me that if more than 1/3 of your computing power is actually allocated to something that's trying to just monitor how well you're doing, you're probably paying too high a price. So we've got a problem. So we have to do better. In today's talk, I will talk very briefly about a trading system, and then I'll focus on what we did to actually solve our problem to bring down the CPU usage for just monitoring the performance of our system. So a trading system is required to be able to handle heavy traffic of requests with ultra low processing latencies. The core piece of a trading system is its matching engine. Inside the matching engine, there could be many concurrent Go routines that are executing different tasks. However, for correctness, every one task is single-threaded and executing in a very strict sequential manner. So in order to achieve high throughput and low latency, the Go routines inside the matching engine have to be conscientious about the CPU usage and use only the amount of CPU that you absolutely need. Pre-allocate memory so that we reduce heap allocations. And in order to not to be scheduled off of CPU by Go scheduler, we should also try to avoid any blocking situations. statsd is the library that we use for monitoring our system performance. We use the statsd client to instrument our application, deploy an agent as a server on the same host. When the stats are collected, they are sent through UDP or Unix domain socket to the server that's deployed on the same host, and the stats get further aggregated and later forwarded to the system monitoring system backend. Inside the trading system, this is how we use the statsd. We use its count method to figure out, like, for example, how many requests have been processed. We use gauge to find out at any point in time how many requests are waiting in the queue. And we use distribution to find out the distribution of the latencies that we're measuring. So in order to solve the problem, we wanted to bring down the usage of CPU time. We first have to make sure that we're doing everything right. So there are many good features of the statsd library that we're using. We want to make sure that we're using it the best way we can. The first thing that we do is that we have to be sure that the client-side aggregation is turned on. Those good features, by default, they're not on. So this will, when we turn this on, not every time a metric is collected, a UDP packet is sent. So this can reduce client-to-server traffic. We also should make sure that we turn on the channel mode so that the application won't block. So it's asynchronous whenever we collect stats. There's a caveat here. When you turn on the channel mode, application is not going to block. It will just give the stats to the statsd client. However, if your channel length is not configured right, the stats will just simply get dropped. So we need a monitor to configure that properly. A buffer pool is also implemented in the library. So this actually reduces memory allocations and later garbage collection pressure. But we also need to make sure that we configure this properly so that we really, truly reach these zero allocations. So having done all of the above did help us. Our CPU usage came down quite a bit, but we wanted to do better. This might be good for a lot of the use cases, but for a trading system, when high throughput and low latency are required, when time equals money, we have to try to do better. So we went inside the library to try to identify areas for improvement. We identified 3 areas. We identified that we could do better on CPU usage and memory allocation when we collect metrics. We identified that we can avoid a concurrency map accessing issue, and we also changed the implementation of the buffer pool to get a lock-free buffer pool for better performance. So dynamic tagging is an important feature for statsd library for the granularity of metrics. However, tagging in this library that we use is only supported as a parameter passed to stats collection APIs. So this actually forces a string slice to be created on the fly. While it might not be a big deal for a small string slice to be created for invoking a function, imagine if this gets executed tens and thousands of times per second. And further, inside those methods, each time when the metric collection is invoked, a concatenating operation is getting executed to concatenate name and tags into one string as the map key. And this also gets executed tens of thousands of times. The solution that we address this is to introduce this metric handle. Metric handle is actually an integer that gets returned by the register metric function that we added. So it basically just creates this association between the name and tags of a metric and its handle. And then by doing this, we make it also the application's responsibility for maintaining this association. Note that the concatenate function is actually invoked here to generate this metric handle. But instead of getting executed over and over when metric collection is happening, this is only happening once at the registration time. And with that, we have new APIs that are, instead of passing a name and a slice of tags, we are only passing handle. Map is actually used for storing all the stats within a metric type. So whenever the application is running, metric is getting collected. It comes in, and we'll check if this metrics exists in the map. If it does, if it does, then we actually find the metric that's pointed by the key, and we do the metrics collection, incrementing the counter and all that. But if it doesn't exist, then we actually needed to create it. So since reads and writes are mixed together, we use a read-write mutex inside this map to actually guard writes and from reads. However, we actually we argue that for metrics collection, there is a phase. There's a write and read phases are separated. There is a phase when the metrics come in for the first time, and we needed to save them in the map. And then later on, during the operation of the application, all the metrics have already that want to come in have already come in. So then we argue that that's just a read phase. So the solution for that is to introduce an immutable map. The immutable map is introduced based on the fact that we can separate the read phase from the write phase. So the write phase is the registration times. During registration, all the metrics are getting registered and stored in the map. And when that is done, and that's done to the regular mutable map. When that is done, the immutable map gets set, a copy of the mutable map, and then the read phase started. So now, with reads and writes being separated, we no longer need locking. Since we are not acquiring and releasing the read, releasing the read, even though the read lock is fast, but repeatedly acquiring it and releasing it adds up. So now, since we are not doing the locking, we're doing less. and less is more. Lastly, we found that the buffer pool implementation of the original client library is suboptimal in that it's using a Go channel for its implementation. And as we know, in the channel implementation, a lock is maintained. So the operations of send, receive, and lend might potentially content for the lock. And further, all the elements inside the channel are actually a pointer to a data struct. So whenever we get an element from the channel, we're getting a pointer, and then we needed to go into the memory to actually bring out the data, which is not optimal. What we did is we replaced this channel implementation with a disruptor implementation for the buffer pool. Disruptor is an idea we borrowed from LMAX disruptor. So it's basically a concurrency framework with a writer and one-to-many readers over a rim buffer. So with this structure, no contention for locks at all, since writer and readers simply just work at different indexes of the rim buffer. And now all the elements we put in the rim buffer are not pointers, they're the actual data. So when the rim buffer is initialized, it's initialized with a sequential space. So the later reads are reading sequentially, and that's more efficient. And lastly, of course, just as the original client library, if we configure the rim buffer size properly, then we can truly reach zero allocations. Our benchmarking results showed a rough range of 5 times to 50 times improvement. So the CPU tax that I showed earlier, which was at 35%, after we have done this careful observing instead of just casual observing, has dropped to 5%. So obviously, we're still paying a price for observing our system, but hopefully it's a small enough price that we can make Heisenberg proud. Thank you for your time. And